Okay, thanks, Guillermo. Thanks for inviting me to give this talk. I was quite uncertain about this talk. Most of my experience is talking to mathematical logicians. So I made an attempt to try to appeal to everybody, but please don't hesitate to stop me during my talk and ask questions. All right. I want to start talking about things that might seem initially like they've got nothing to do with each other. So I'd like to remind you what computably enumerable sets are. And so I'm going to start with the notion of computability. It was formalized back in the 1930s and 40s by various people working, Church, Turing, Kleene, others, defining the class of what it means to be computable for, say, a function from the natural numbers to the natural numbers. And it's a robust notion in the sense that there are many, many, many equivalent characterizations. And I'm not an expert on the philosophy, but some people have the opinion that Turing's paper in particular gave a convincing argument for why this is the notion that we should use when we try to formalize what computable means in mathematics. And of course, computable here means with no bounds on time or space. It's not resource bounded in the style of computer science. And here's a simple definition. A computably enumerable set is a set that is the range of a computable function. But that's not exactly how we think about it in practice. If you take a computable function f, I'm defining a sequence of sets, a sub 0, a sub 1, a sub 2, a sub 3. And all of these sets are finite. The a sub s is written, it's just the collection of the first s, I get +1 values of the function. So each one of them is a finite subset of the range of the function. And if I take the union over all s, then I'll get the sets, the whole range of the function. And we're thinking about it as a dynamic process going on. I would regard this definition as something that is sometimes called static, using Boolean combinations, functions, etc. But here that we have a process that we think of as happening a long time. Before stage 0, nothing happens. I have a big basket and there's nothing in it. And then I run a computation and find out what f of 0 is, and I throw the number into the basket. And then f of 1, and I throw that into the basket, and my basket gets bigger and bigger and bigger, fuller and fuller and fuller with numbers. And that's the dynamic process. If we think of the value f of s as the number that goes into the set at stage s of my process of enumeration. And those sets happen to be the same as semi-decidable. I won't go into the details of that, but you think about it like the question is 13 an element of the computably enumerable set? And the answer is, well, maybe, I don't know, but it's not necessarily a decidable question. If it is, then I will see it is at some point. But if it's not, then I'll never be sure, right? The point is that the function f is not necessarily monotonic. It's not increasing. I could have very large numbers go into the set and then a small number go into the set. Let's switch tack. Topology. Talk about the real line for a second. The notion of an open interval, just the collection of numbers strictly between two numbers, right? So it doesn't include the endpoints. That's quite important. A set is open if it's the union of open intervals. But in fact, I can assume that those numbers a, b, that are edges of the endpoints of those intervals are rational numbers rather than arbitrary real numbers. The point being is that because the rational dense inside the reals, each open interval is the union of subintervals with rational endpoints. So in the definition of open set, I could change the definition to say the union of rational open intervals where both endpoints are rational numbers. And why do I care to make this difference is that the collection of rational numbers is countable and the collection of real numbers is not. And therefore, there's only countably many rational open intervals, but there's continuum many open intervals. So take an open set, and I know that I can write it as the union of rational open intervals. There's only countably many rational open intervals, so it's the union of a countable set of rational open intervals. So I put them on the line: first interval, second interval, third interval, fourth interval, and so on. The nth interval is AS, BS. And now I take just an arbitrary real number. I see I wrote, let's assume that it's in the unit interval just to ease up notation. There's nothing important about that. So I can write it out. What's a real number? I'll take your favorite definition, but the way that we think about it, it's, you know, it's something that I can write by point and then an infinite string of digits in whatever base that I like. Let's take base 10, why not? So at every step, I can look at 0 point first digit, 0 point first two digits, 0 point first three digits, and so on. And that is a sequence that converges in the sense of topology of the real line to the real x. And moreover, I know how quickly it converges. The distance between the rational that is determined by the first s bits is no more than 10 to the minus s away from my real x. So if I want to answer the question, is this real in this open set, I can look at those rational approximations and look at stage S at the first S intervals whose union is that open set and check for each one, are you in, are you in? And for rational numbers, that's an immediate question. I get immediately the answer yes or no, because rational numbers are coded by finitely much information. I can answer all the questions about rational numbers with absolute certainty. Now, of course, if the approximation is in the open interval, but it's too close to the edge, then it doesn't necessarily imply that X is the open interval, but I can kind of like take a decent security barrier and not commit until I see it in the open interval and sufficiently far away from the endpoints to guarantee that I will never be able to leave this interval, and therefore X is in this open set. So each step of this process can be carried out in finite time. I'm checking, you know, a rational number with finitely many digits, and I'm checking finitely many rational open intervals. And if the answer is, if X is in, then I will eventually know that it is in. But if it's not, then I'll never be sure that it's not. Right? Now, disclaimer before you crucify me, I'm lying to you throughout. I'm not actually talking about the real numbers. If you like, I'm talking about the irrational numbers, right? Which are homomorphic to bare space where I am actually living, but never mind that. The difference is that a real number doesn't really determine, like there's no exact bijection between the decimal expansions and the real numbers, but that's only a problem on decimal rationals. So let's ignore those. Okay. Something back to computability. Turing not only defined his Turing machines, he also introduced what is known as Oracle Turing machines. So these are machines that have an access to a black box into which I can store whatever amount of information that I like. And the point is that it doesn't have to be computable. And computations of those machines run exactly the same as computations of Turing machines run. But from time to time, one of the steps of the computation could be, I've written a number on my tape, ask the Oracle what is the value of the function on that number, and the Oracle will give you the answer immediately, and you'll be able to keep going. So this is a notion of computation, and it leads to a notion of Turing reducibility. I won't actually at all talk about Turing degrees in this talk, but if I'm defining Oracle computations, then I should define Turing reducibility, and I should then tell you about Turing equivalence, but don't worry about it too much. Right? The interpretive option, if I had F as input, as something that I know, what else could I know? G reducible to F means, you know, nobody can actually know F, but if you did, you'd also be able to calculate G. the important part of that is that if G is Turing reducible to F, and there's some Oracle machine that does the calculation on every input, particular input, I want, you give me 5 to calculate G of 5. What I need to do is, I run the machine, and the machine does its thing, and it'll halt. And that's part of the requirement that it does compute the correct value. It halts, and the correct value is written on the tape. Each one of those computations takes finitely many steps. That hasn't changed for a notion of computation. And that means that there's only finitely many queries that could have happened to the Oracle during that computation. Every query to the Oracle is a step. That means there's only finitely much of the information for the Oracle that I actually need in order to carry out this computation. And finite times finite is finite, so if you want to ask finitely many values of G, I need finitely many values of F to be able to carry out the computation. As the input grows, I might need more and more and more and more of F. That doesn't mean that I don't need all of F for the entirety of G, but for every particular value, for finitely much information, I need finitely much information. What's a continuous function? Well, the top bullet point is the familiar definition that you might see in a real analysis course or a calculus course. The second bullet point is an equivalent definition in terms of topology. But really, what is a continuous function? A continuous function is a function where the finitely much information about the target, the value of the function, is determined by finitely much information about the input. Right? So if I have a continuous function and I have a real and it's given to me via its decimal expansion, and I can look at my sequence of rationals approximating this real taken by cut off the expansion at a finite step, and saying this is my QS, my 10 to the minus s approximation for the real that I'm actually interested in. Right? I can ask for each rational interval, I can I think what I wrote there is not quite correct. But there should be an if there and the square bracket, sorry. The point is that if I have a finite approximation, and if the continuous function has already committed via this epsilon and delta, this entire neighborhood of this rational is mapped to into some small neighborhood of some other rational, then I know the value, approximately the value of f of x. And the point about the epsilon delta is that you can get better and better approximation for f of x by giving better and better approximations for x. Okay. And again, from finitely many bits, no, it's not bits, it's not binary, finitely many digits of x, I can get finitely many digits of f of x. Not necessarily the same number of digits. I might need 100 million digits of x just to calculate the first digit of f of x. But as it goes to infinity, you never get stuck. Reductions. Back to computability. There's a notion, it's a strict notion of relative computability. What is M reducible? I always feel very embarrassed for my field by this terminology and notation. It is what it is, M reducible. Again, it's a notion of I have some non-computable information, what else can I calculate from it? In this case, the procedure of reducing is very, very narrow and specific. I'm only allowed one query to the Oracle, and I have to report the same answer. So it's a question of translation. I have a question that I don't know how to answer. Membership in A. Is a given number in A? Don't know. But I have a computable way of translating this question to ask a question about a different thing that I also can't do. But this process of translation tells me that there's some kind of connection between those two things that I can't do. The second one, if I could do the second, then I can do the first. So here's a very silly example. The set of codes of Turing machines that halt on the input 0. That's a set of numbers, that's my A. Set of codes of Turing machines that hold on all inputs. That's a set of numbers, I call this B. Now, what's my reduction? I'm going to say that A is M reducible to B. What's my reduction? I get a code of a Turing machine. Right. And I output a code of the Turing machine. And to do that, I need to tell you what this other Turing machine does based on what the input Turing machine does. And what the instructions for the second Turing machine's f of E is raise the input, write 0, and run this one. And so the behavior of f of E on every input will be the same as the behavior of E on input 0, and I'll get this reduction. Not the most sophisticated reduction here, just to give you a taste and example. This is often used in basic computability courses and proofs of non-computability, right? Because if A is M reducible to B, and B is computable, then A is computable. So we do the counterpositive. We know that A is non-computable. To prove the non-computability of B, we reduce A to B. It would work for Turing as well. It's just that the natural examples are usually M reductions. Same idea in set theory. Appeared much later in set theory, notion of reduction between sets of real numbers. And the definition is exactly the same as M reducibility, except that instead of computable functions, I write continuous function. Here's again a silly example. A now is the set of x's where when I write the decimal expansion, somewhere I will see 5. There's no decision procedure to take a real and answer this question, because that 5 could happen very, very late or maybe never. In the set of reals that not only the number 5 appears, it appears infinitely often, and even more complicated. And my reduction is my continuous reduction. Continuous reductions give me finitely many bits. I'll output finitely many bits. So I'm looking at the bits of x, x0, x1, x2, and I keep going and I just say output 0, 0, 0, 0, 0, 0, until I see a 5. Then I change to 5, 5, 5, 5, 5, 5, 5. Right, so if x doesn't have a 5, what I will output is the number 0, like 0.00000. And if one of the x's is a 5, then eventually I will see it, and I will switch from 0, 0, 0 to 5, 5, 5, and for the rest of time I will put down 5, 5, 5, 5, 5, 5, 5. And so certainly it'll have infinitely many 5s. Even better, it'll have cofinitely many 5s, all but finitely many of the digits are going to be 5. In both cases, for example, to say that something is significantly more complicated, then what you need to do is to show that there is no reduction in the other direction. For example, in this case, B is strictly more complicated than A. I can reduce A to B, but I cannot reduce B to A. Okay, so these are all kind of like seems like analogies or things that smell the same. Is there a more solid connection? And the answer is absolutely yes. So first of all, I want to write the notion of an effectively open set. So remember, rational numbers are things that are coded by finitely many information. I can manipulate them immediately via coding. And so I can talk about a computably enumerable set of rational open intervals. There's going to be a computable function f, such that on input s, it would tell me the codes of the endpoints of the interval. And if a set is the union of something like that, I call it effectively open. And I will call a function from the real numbers to the real numbers computable. If passing from bits of x to the bits of f of x not only can be done continuously, but computably so. Right, I will start reading x, and there's going to be a computable function that is going to, at some point, say, oh, you've shown me enough of x, I'm going to tell you what the first digit of f of x is going to be. And instead of just being an arbitrary function, it's going to be a computable function. And then, of course, call this function effectively continuous or computable. Here's what I've been saying just slightly more formally. Right, the set is open if there's a function g, g is not a function on the reals, g is a kind of countable object, it's a function on numbers, on natural numbers. It's equivalently, it's defined on finite sequences of digits. And so what this function g is says, what it does, it says I've read the first as many digits of a possible input. Don't know what about the rest, but I'm going to make a guess about whether it's in the set or not. And the set is open if I can do this in a very particular way. Along every sequence, and I'll probably start with guess out, which is the value 0. I'm computing the characteristic function of the set. And as I'm reading the bit, I'm reading like, what's your guess based on the first 1 digit? What's your guess based on the first 2 digits? What's your guess based on the first 3 digits? And what I'm allowed to do in this process is only guess no, 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 no. Maybe change my mind to yes, then I'm not allowed to change my mind anymore. And it's in if and only if I change my mind at some point. And it's out if I never change my mind and I just keep outputting no, no, no. The set is effectively open if there's a computable function g with exactly the same properties. Now, the notion of relativization is central to the connection of computability and set theory. Again, using the notion of an Oracle Turing machine, I told you what it means for a function to compute another function. Well, now I can look at the ranges of all the functions that I compute. That's a collection of sets. And those are the things that are computably enumerable relative to the possibly non-computable information that sits in the black box of the Oracle. It's a notion of a set that is computably enumerable relative to an Oracle. And if I have that, then I just copy over the definition and I say what it means for an open set to be effectively open relative to some Oracle. Okay. The point is that every open set is effectively open relative to something. Because remember, to completely determine what an open set is, that's countably much information. Right? A list of rational open intervals whose union is the set. Look at that list. That's countably much information. I can code it up by a countable object, like a function from natural numbers to the natural numbers. So every open set is effectively open relative to any Oracle that codes any, well, sometimes called a code for the open set, but a list of intervals whose union is the set. And similarly, the same thing we can do with computable functions, computable relative to an Oracle, and continuity is the same thing as effective continuity relative to some Oracle. And this connection brings into descriptive set theory a plethora of tools from computability. So not only we can say finer things, but we can use techniques from computability to prove things about descriptive set theory, and also sometimes the other way around. So I want to talk a little bit about one aspect of this. Again, I'm not gonna actually, I don't want to go into gruesome details, so this is going to be all very hand-wavy. But here's a kind of like very grand, ambitious problem. Right? So we defined Wadge reducibility between sets of reals. A is reducible to B if it is continuous, reducible to B like M reduction via a continuous function. There's lots of sets of reals, right? 2 to the continuum many. But the point about this reducibility is that just like Turing, I can have a notion of relative complexity. 2 things are kind of equivalent if they're reducible to each other. And one thing is significantly more complicated than the other if this is reducible to this, but not the other way around. And there's a whole universe out there of 2 to continuum many sets. And the question is, what does this picture look like? And remarkably, unlike the Turing degrees, the picture is very, very orderly. So for example, we know what the partial ordering looks like completely. It looks like, yes. I'll get to what all of these symbols mean. but it's kind of like, by more complicated, I mean further up. So all of these correspond to various kind of classes of sets of reals that are all equivalent to each other. So these are Wadge degrees, just like Turing degrees, equivalence classes under Wadge by reduction. But I want much more than just telling you what it looks like, just a sequence of dots. I want to, like, can you give me any kind of like big encyclopedia that kind of, or telephone book that lists them all? And questions are necessary, like these are necessarily partial, but not so much because 2 to the continuum is really big. But even if you look at Borel sets, then you get something that is really, really interesting. And that's, so I'm just listing a bunch of names of people who gave various kinds of answers to this question, partial answers, extensions to answers, answers of very different kind of styles. But I want to give you a taste of what's going on. Arithmetical hierarchy, for example, on the reals, is a class that starts with open and closed, and then alternates by taking countable unions and countable intersections. In terms of picture here, I want to write a dot here. This is the collection of all open sets. This is a collection of all closed sets. Now, when I take unions of countably many things of those, this is something that is called sigma 02, and analyst topologists sometimes will call it if sigma, if standing for closed and sigma denoting countable union. And the complements of these things are also the things that are intersections of countably many open sets, also known as G delta. And then I can keep going. Take countable unions of these. Take countable unions of these. And so this is a hierarchy of sets of reals that get more and more and more complicated. I draw it this way because in terms of containment, these are incomparable. But it's not the case that every open set is closed, or it's not the case that every closed set is open. But I've got anything up is a div. So every open set is both G delta and F sigma. And this pattern repeats. So here's a result of characterizing one particular kind of Wadge degrees, the sigma n things that are not pi n. Right, so each one of those dots, if I only count the things that are properly here and do not appear anywhere else lower down, do not appear here, that's not a class in the arithmetical hierarchy, that's also a Wadge degree, which is a much stronger result. Any 2 of these sets, there's a continuous reduction from one to the other. Would be really nice if, and you can see that there's a kind of nice mirroring here. Maybe these are all the Wadge degrees of arithmetical sets. Sadly, that is not the case. But effective arithmetical hierarchy, I can define exactly the same thing. Instead of starting with open sets, I start with CE sets or with effectively open sets. Then I have to be careful about the kinds of unions that I take. I can't take arbitrary unions because that would be too big. I take unions of uniform. So for effective G delta, I need to take the intersection not only of a sequence of countable sequence of open sets, but if they're all required to be effective, but not only just each one of them is effective, not like I have a set G, which is the intersection of U0 intersect U1, intersect U2, etc. For each one, there's an algorithm that enumerates rational open intervals that generate it. I want a single algorithm that does it for all of them. Right? A single algorithm will take an input, an index, and give you an enumeration. But that's really what uniformly CE is. The reason for this notation is that it relates to definability in the standard model of arithmetic, right? So Gödel showed that CE is the same thing as definable via existential formulas, where instead of quantifier free, you use bounded. And then the hierarchy of alternating quantifiers definability by these kinds of formulas completely corresponds to the effective arithmetical hierarchy. And the same thing that I said, open is effectively open relative to an oracle that works at every level of this hierarchy. I didn't give you this entire picture because there's another class here. The delta class, which is just the sets that are above. And so now I'm going to, my line has reached incredible proportions because this is a collection of all Clopen sets. In their space, there's lots. On the real line, there are none. But weight theory works nicely on zero-dimensional spaces. If I look at the computability side, then delta 0 and is familiar. Those are just the decidable sets of the basic theorem that if I can have a set and I can enumerate it, and I can enumerate its complement, then I can decide. I'll ask is 5 in, run the enumerations, it'll show up in one of those sites. Then you'll know. There's a nice characterization of this class here. Again, and what I want to emphasize is the dynamic nature of this class. This class, as it's defined, is defined by a static definition, a Boolean combination. It is a set which is both the union of countably many open closed sets and also the intersection of countably many open sets. It doesn't tell you how to decide, guess or approximate whether a given number is in. And there's a particular way of doing this. It is, again, a guessing function. Right, so now I'm going to have a function defined on finite sequences of digits. And it's going to guess either in or out. But unlike the open set case, I have complete freedom in changing my mind as long as I eventually settle down. Along each real, I need to eventually guess correctly and then never change my mind anymore. But there's no a priori bound on how many times I'm allowed to change my mind during that process. And that characterizes delta 0 too. For sets of natural numbers, this is known as Schoenfeld's limit lemma. How do we deal with computability with higher levels of this hierarchy? Because these sets get really complicated very quickly. The answer is we've got a tool which is much more easier to work with in computability rather than set theory, and there's a tool of the Turing jump. Easy to define. Take an oracle, look at the collection of all oracle machines, answer the halting question. Does it halt or not? If I feed that oracle to the machine, then that's a set of natural numbers, the collection of indices of Turing machines. Coded as a real number, that's the jump of the input. So I can think of it as a function from the real numbers to the real numbers. The input really is an oracle and the output is a set of natural numbers, but I want to think about them as objects of the same type. So everything is coded by real numbers. And there's this theorem, effective version due to Post, both-ways version due to Gwaltowski, is that I can reduce, right, sigma 02 to sigma 01. I can't do that by continuous function. Sigma 02 is strictly more complicated. Right? That I told you that this is a wage degree and this is a wage degree. There's no reduction from here to here. Sets that are properly sigma 2 cannot be continuously reduced to sigma 1 sets to open sets. But the jump function is not continuous. It's very much not continuous. It's nowhere continuous. It's not continuous relative to any oracle. It's the most complicated Baire class 1 function. So that allows me to reduce complexity. I'm just allowed to take jumps. And I can keep going, iterating up. Take the jump again, and I'll get sigma 3, and I'll get sigma 4, and I'll get sigma 5, and so on. So everything in that sense is reducible back to open sets that are much easier to understand, and then the two sets that are much easier to understand. So for example, how do I understand delta 0, 3? If I just look at approximation along inputs, that's really complicated. But if I'm taking the jump, I've reduced the quantifier complexity by 1, and now I'm back in the case of delta 0, 2, and there I know what to do. But the jump allows me to talk about approximation procedures for sets that are more and more complicated. And in fact, I can go all the way up to omega 1 in the Borel hierarchy. Let's go a little bit finer. So I just remind the first 2 bullet points of things that I've already said. The set is delta 0, 2, the limit lemma, delta 0, 2 if and only if I can approximate membership in the set along initial segments of a real that eventually stabilizes on the correct output, or correct answer. No restrictions on the kind of approximation otherwise. On the other hand, open sets are things like that. Right? Every open set is delta 0, 2, so every open set has this kind of computable approximation, but it has a computable approximation of a very particular kind, like the one where I have to start with 0 and then make it change to 1, and then not allowed to change my mind ever again. And you can have lots of things in between. For example, what's the next more complicated class? Let's say that you start with 0, allowed to change to 1, then extra freedom, you're allowed to change back to 0, but then that's it. Okay. What are the sets that have these kinds of approximations? And the answer, these are exactly the Boolean differences of 2 open sets. Right, because if I have 2 open sets B and C, you can think of the approximation of, I haven't gone anywhere yet. Then maybe I go into B, and now I think that I'm in the set difference B minus C. But then maybe I go into C, and I'm kind of thrown out of B minus C again. I can do this 3 mind changes, 4 mind changes, omega mind changes, omega plus 1 mind changes, and so on along the ordinals. And that will give you all the Wage degrees inside the class delta 2. All right, so this little picture here in the arithmetic hierarchy, if you look at the much finer distinction as to Wage, or continuous reducibility becomes this tower of omega 1, but it kind of looks like this, right? Open, closed, open. 2 CE differences, or 2 open differences of 2 open set complements of these 2 co-CE. 3 CE, change your mind 3 times. Difference between the set and the complement is where you start your guess. Here you change your mind 3 times what you start within. And then there's the intersections of those. Those are all the Wage degrees inside delta 2. And it's a theorem of Hausdorff that every delta 2 set is like that. And then work of Wadge and others shows that that actually exhausts. So this is a really good answer to the original question, at least for delta 2 sets. I can tell you exactly what the Wadge class are. Each one I can give you a name and an address. I can tell you which is contained in which.
Sorry, in the previous slide. Can you just spell out a bit the last bullet point?
That's finite.
You extend
the difference
to omega. I mean,
the difference hierarchy. Well, okay, so it takes a bit of a reworking, but let's rephrase this. What is 3CE? I have the sequence. I might as well say that they're contained in each other, and I'm walking down the ordinal. So I'm starting saying, don't know anything
Okay.
yet.
Okay.
Then maybe I go into this and I say yes. Then maybe I go into this and I say no. Then maybe I go into this and then I say yes. For omega, you just have an omega sequence and you fall down. So it's still a finite, it's omega, it's an infinite ordinal, but you're counting down the ordinal, so it's finitely many multiples.
All of those are all in delta 2.
Yeah. Right. If all of these A's are open sets. Right. So that's the difference hierarchy based on open sets. Right, so that's every Wadge degree in type delta 2 is determined by the difference hierarchy. If I'm the difference of two open sets, two things that are differences of open sets, they're in this class, but they're not in this class, then they're Wadge equivalent. Okay, and that's true for every level of the difference hierarchy. Beyond delta 2, things get more complicated. Essentially because I can play with the jump and also not use the jump sometimes. So the Hausdorff-Koltowski theorem says that every set in delta 3 is an element of the difference hierarchy where I start with sigma 2 sets instead of sigma 1 sets. It is kind of like the jump of the difference hierarchy, but that doesn't exhaust the Wadge degrees there. And so I need a more detailed analysis. Such a more detailed analysis exists. The last bullet point here gives you the order type of, after identifying things, if I want to press this into a well ordering, then I get a well ordering with an order type. Inside of the order type is omega 1, the least uncountable ordinal. For delta 3, every level of the difference hierarchy, inside it sits another like omega 1, and it gets worse and worse. It's not omega 1 times omega 1, it's omega 1 to the power, ordinal power omega 1, and so on. Veblen functions are involved. Okay, so now that I understand, like this is the only new thing that I'm going to tell you today, is that we developed 4 Borel sets, which are these things, but when you go all the way up to omega 1, we can get a system of descriptions. And it has some resemblance to other systems of descriptions for Wadge degrees of Borel sets, but we really emphasize this dynamic aspect of it. So our systems in general would be, our descriptions would be kind of approximation processes within approximation processes within approximation processes, right? So that they will eventually be coded by well-founded trees. So I'll start at a root, and then I'll have many cuts, possibly countably many ways to go. And the question is, which one should I choose? This is something that will have an approximation process, and the description will give you the exact order on how many times you're allowed to change your mind. And then one of those, and so each one of those nodes will tell you how many times you're allowed to change your mind and how many jumps you're allowed to take in order to answer the question. And once you've taken a jump, you can't undo that. So the jump levels have to non-decrease. But it's a well-founded tree, so along each approximation, I'll eventually reach a leaf, and the leaf will tell me in and out. And that's the most general description there is for Wadge degrees of Borel sets. Advantages of these systems of descriptions, they're given to you. A lot of system of descriptions will say this is a description, and manipulate these in these particular ways, you'll get another more description. So it's an inductive definition of descriptions. These are, you get all the information right there. And that allows us to reason about classes using description. So this is very much logic, whether you like it or not, right? Language is the object, like is an object under investigation, and we're investigating the connection between language and the objects that they describe, right? So there's a description of a class, mathematical object. There's a class that is described. Given 2 descriptions, do they describe the same class? We can tell you. There's a characterization. given a description. Does this class have this particular property? What is its order type in the wage hierarchy? All of these things we can learn by looking at the full description. And moreover, these same techniques apply not only to sets of reals and wage reducibility, they apply to something as known as Sullivan's fine hierarchy, where it looks exactly the same, except that you're looking at effective reductions, m degrees, and you're looking at sets of natural numbers. What I haven't told you about, well, a lot of things. Lots of things that I don't know about, so I won't tell you about them. But that's far from it about applications of computability to descriptive set theory and vice versa. There's things that continue this line of investigation, things like reverse sample-more separation theorem, or use a priority argument in order to prove a theorem of classical descriptive set theory. But then there's things that are completely in different direction. Like we look at looking at continuity in terms of effective computability. We can ask at some level of computability, what does it take for, and we can ask measure question, what does it take for a point to be differentiable, to be a point of like every computable function will be differentiable relative to it. So there's work of Andre and Joe Miller and Vasco Bratka on this codic theory. More recently, work on geometric measure theory, understanding the Hausdorff dimension of a set based on approximations like effective dimensions of individual points and containing these together. So that's been in the news recently, in our news. But I think I should stop here. Thanks for listening.